A furnace heat exchanger survives 15 years of heating your home by cycling between 1200 degrees Fahrenheit and room temperature roughly 10,000 times. The metal cracks not from rust, but from the same fatigue that snaps a paperclip after enough bends. By the end of this, you'll understand exactly why the crack is inevitable, why manufacturers can't just use thicker steel, and why the failure gives you no warning until a detector catches it. Start with the part itself. A clamshell heat exchanger is a thin steel shell, often less than a millimeter thick, folded into a series of cells that gas flows through as it burns. That thinness isn't a manufacturing shortcut. Thin steel heats up fast and transfers heat to the airstream fast, which is exactly what makes a furnace efficient. The thicker you make that wall, the slower heat moves through it, and the more fuel you burn to deliver the same warm air to the house. What matters here is the actual temperature swing that metal endures every single cycle. When the burner fires, the surface facing the flame jumps toward 1200 degrees Fahrenheit within seconds. When the thermostat is satisfied and the burner shuts off, that same surface falls back toward room temperature, sometimes in under a minute with the blower still pushing air across it. Steel expands when heated and contracts when cooled, and it does this unevenly because the flame side heats faster than the back side. The reason this matters is not the heat itself, it's the mismatch. One section of metal wants to expand, while the section next to it hasn't caught up yet, and that mismatch creates internal stress at a microscopic level, concentrated right at the seams and welds where the geometry changes. A furnace fires and cycles off dozens of times a day across a heating season, which is where the 10,000 cycle number over 15 years actually comes from. Here's the reopener worth sitting with. The same paperclip that survives being bent once can be bent back and forth only so many times before it snaps clean through, and nobody sees the internal damage accumulating until the last bend. Metal fatigue works by accumulating microscopic dislocations inside the crystal structure of the steel. And this is the mechanism that separates heat exchanger failure from almost every other appliance failure story. Corrosion eats material away from the outside in, and you can often see it coming as rust or pitting. Fatigue is different. The metal looks completely normal on the surface, while damage builds invisibly inside the grain structure with every single thermal cycle. The interesting part is that fatigue damage doesn't accumulate in a straight line. Early cycles cause almost no visible change at all, which is exactly why a 5-year-old furnace looks and performs identically to how it did on day one. The damage is there, but it's distributed as thousands of sub-microscopic dislocations that haven't yet organized into anything you could detect with a flashlight and a mirror. Around year 10 to 12 for most residential units, those scattered dislocations begin linking up into an actual crack tip, usually starting at a stress riser like a weld seam, a stamped corner, or a spot where two dissimilar thicknesses meet. Once a crack tip exists, it behaves completely differently from the slow, invisible phase that came before it. Each subsequent thermal cycle drives the crack forward by a tiny, measurable amount, because the stress concentrates hardest exactly at the crack's leading edge. The reason failure feels sudden to homeowners is not that the furnace broke suddenly, it's that the crack existed for years below the threshold where it does anything noticeable. A hairline crack that's a few thousandths of an inch wide doesn't leak enough combustion gas to smell, doesn't change the flame pattern enough to see, and doesn't affect heating performance in any way a person would register standing in front of the thermostat. You'd expect the fix to be simple, just make the steel thicker so it takes more cycles to crack. That raises a harder problem because thickness doesn't scale the fix the way intuition suggests. A thicker heat exchanger wall does resist crack initiation longer, but it also absorbs and releases heat more slowly, which drops the furnace's steady-state efficiency rating directly because slower heat transfer means more fuel burned to move the same heat into the airstream. Manufacturers who tried thicker gauge steel in the 1980s and 1990s found the efficiency penalty large enough to fail modern AFUE certification thresholds outright, which made the parts commercially non-viable regardless of their improved lifespan. The industry standard settled on 20 to 24 gauge steel or aluminized steel specifically because it's the thinnest material that still meets minimum service life expectations under normal cycling loads, not because it's the most durable option available. The interesting part is that this is a straightforward engineering trade-off hiding behind a part that most homeowners never see. A furnace that heats efficiently for 15 years and then needs a new heat exchanger is, from a design standpoint, working exactly as intended. The alternative, thick-walled steel that lasts 30 years but wastes 10 to 15% more fuel every single winter for those 30 years, loses on total cost and on regulatory efficiency minimums almost everywhere. Coatings looked like the obvious patch for this problem, and this is the chapter where most explanations stop being honest about why they don't work. Ceramic and aluminized coatings can resist oxidation and slow surface corrosion measurably well in laboratory testing. But the reason coatings fail in real furnaces is not that the coating chemistry is weak. It's that the coating and the steel underneath expand at different rates when heated. That mismatch is called differential thermal expansion, and it means every single time the furnace fires, the coating and the base metal try to grow by different amounts. Over thousands of cycles, that mismatch produces its own microcracking at the coating layer itself, and once the coating cracks, it stops protecting anything and can even trap moisture or combustion byproducts against the base steel underneath it. Coatings extend service life modestly in controlled conditions but don't change the underlying fatigue mechanism because the fatigue is happening in the steel's crystal structure, not on its surface. The part that should worry anyone reading a furnace spec sheet is that the crack, once it fully penetrates the exchanger wall, creates a direct path between the combustion chamber and the air your blower pushes into living spaces. Combustion produces carbon monoxide as a normal byproduct, and in a functioning heat exchanger, that gas is entirely contained and vented outside through the flue. A cracked exchanger lets a fraction of that combustion gas mix into the return air path instead. What matters is the crack doesn't open all at once. It starts as a hairline gap that only separates fully when the metal is at its hottest and most expanded, meaning the leak can be intermittent and only present partway through a heating cycle. This is precisely why some early-stage cracked exchangers pass a cold visual inspection completely, because the technician is looking at metal that hasn't expanded into the failure position. A crack can be present for a full season before it consistently leaks enough carbon monoxide to register on a detector. Real service data from HVAC networks tracking failure callouts shows heat exchanger replacement volume climbing sharply, starting around year 12, peaking between years 15 and 18, which lines up almost exactly with the fatigue accumulation curve rather than with any corrosion or age-related material breakdown timeline. The reason technicians treat any furnace over 15 years old as a mandatory heat exchanger inspection item is that the failure curve is now well documented across enough units to be statistically predictable, even though it's invisible in any individual furnace until it happens. This is also why carbon monoxide detectors near furnaces aren't a redundant precaution. They're the only detection method that catches a failure mode with zero other symptoms. A cracked heat exchanger doesn't reliably produce a smell, a sound, a visible flame change, or a performance drop because the leak is often small relative to total airflow, and combustion gas is largely odorless in the concentrations that matter most. So the 15-year number people hear from HVAC technicians isn't a marketing figure or a conservative buffer. It's the point on the fatigue curve where thousands of expansion-contraction cycles in thin steel statistically catch up to the material in a part that was engineered thin on purpose, coated ineffectively for reasons rooted in physics rather than corner cutting, and built to fail exactly where nobody can watch it happen,